Okay, welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's tutorial is hypothesis testing. And namely, the hypothesis test that I'm going to introduce to you is the t-test. So what we're going to talk about is the t-test. The t-test looks at shifts in the mean result of a process. Okay, so that's what we're going to have a look at. I'm going to just talk a little bit about what a hypothesis test is first, and then we're going to go to the SPC Xl Software, show you how that it deals with it. So let's just talk about why you need a hypothesis test. Why do I need a t-test? Why don't I just look at data and be able to tell what's happening? Essentially, the point where you're going to need a t-test is when you've made a deliberate change to a process. So you've taken sample A, you've decided, so you've taken sample A, you've decided that you have some new idea, a new supplier, a new setting on the machine, and then you take sample B and you see a difference. And at that point, because you see a difference, you think your idea, your new setting, your new speed, your new supplier, that was what created the shift. Okay, so that's the point at which you need a hypothesis test. Why do you need a hypothesis test? Well, it's like this. Imagine you have a bin of components. Okay, we'll say that let's say there's 10,000 in the bin, and you are interested in some feature of that component. So you take a sample. We'll call it sample A. We'll say you take 50 pieces and you measure that feature. So it could be the length, the diameter, whatever it happens to be. So this would be measurable data that we're talking about here. And you use the results, obviously, to try and assess what's going on in the bin, what's happening in the other 10,000, what's happening in the other 10,000 pieces. But if you took another sample out of the same bin, so now we'll take sample B, we'll take another 50. When you measure the same feature and you work out the average result, would you expect to get an identical set of results? Or an identical average even? Well, no, of course not. It's two samples. So you see, one of the problems with suggesting that when two samples are different, that is the indication of a shift in the process. Actually, that isn't true. When you take two samples, even from a static process, and of course in this case, this example, because the data set here is very, very static. The process isn't moving. We've got one bin. We've got one bin of parts here. So this is a static process. And yet, the two samples are different. Now then, is that an indication that the process moved in between our two samples, or was it just two samples? The only way you can judge that is to do a hypothesis test. So what a hypothesis test does essentially is it looks at the data set in two possible ways. It looks at the data set like this top one and assumes that the two samples have come from the same distribution. In other words, your new idea here, when you're taking your two samples, you will have put a change in between sample A and sample B. It looks at the process and says, well, let's look at them as if they're the same. Let's look at them as if there's been a genuine shift in the mean of the results. And what it basically does is it says, well, look, if this situation is really at play, if they really are two samples from the same distribution, what is the probability that two samples would be this far apart? and it works out a probability value for you. And if this probability value is really small, so the probability of two samples from the same distribution being this different from one another, it's a really unlikely possibility, then we are going to assume not that they are samples from the same distribution, but actually they are two separate distributions. And that's the way a hypothesis test works. It generates what's known as a p-value, and we are looking for the p-value to be small. A great way to look at the p-value, it is your probability of being wrong if you conclude that your new setting made a difference to the process. And of course, because it's the probability of you being wrong, you'd like it to be very small. Okay, so let's take a look at this in software. So we'll flick across to Excel now. I've got the two data sets that you just saw on the page there. So let me just take that back a second. We'll just take a look at that. So I've got these two data sets, look, and the scenario is that the engineer thinks that the temperature makes a difference. He's taken 9 samples at a low temperature, 200 degrees. He's taken 9 samples at a high temperature, 300 degrees. And of course, there's two possibilities. This could be the possibility that the process is just 2 samples from the same distribution, or it could be that 2 separate distributions, and therefore temperature does make a difference. Okay, so that's what we're trying to answer. Does temperature make a difference? Did it really create that shift? Oops. Let's go back to Excel. So we've got the two data sets. I've just put them in 2 columns. You could put them in rows. It really doesn't matter. And then what I'm going to do, I'm going to go to the analysis tools on my list, and I'm going to do a t-test. And look, it says t-test matrix mean in brackets. In other words, we are going to test whether the average has been shifted by a change in the temperature. Okay. Now what I'm going to do is highlight the data set. This is a standard way of using SPC Xl. Highlight the data set. Select the tool. Then says, is that the data? Yes, it is. Okay. It then says, well, how did you put the data in? Did you put it in columns or rows? Well, I put it in columns. Click next. Then it says, well, okay, what would you like to know? Do you want to know if they're just not equal to one another? Do you want to know if one's greater than, one's equal to, greater than, or one's less than the other in terms of the shift in the mean? Now, I don't care which way the mean's gone. I just want to know where the temperature made a difference. So it doesn't matter to me. So I'm going to go not equals to. All right, so I just want to know that there's been a shift. Click go. And then you get this p-value. There it is, 0.035. The way to look at that is there is a 3.5% chance that this result would happen just by luck alone if the process really hadn't moved. Yeah, so you've dipped into the bin of parts, this result would out, and if you did that 100 times, so if you dipped into the bin and bought out pairs of samples and you bought out 100 pairs, only 3.5% of those samples would be this different to one another. Now, because we've seen quite a rare event, and we've seen it with the very first sample set that we've taken. Therefore, what we are going to assume is not that this was just a lucky draw of 2 samples and the process has not moved, but because this number is 0.035, we are going to conclude that our new temperature created that shift. Okay, so the value that you're looking for, it's known as the alpha value. The alpha value you should be looking for is to beat 0.05. So in other words, there is only a 5% chance of this result happening by luck alone. In other words, it wasn't luck, it was your shift that created it, more than likely. Okay, now then, an important thing to point out about this number here. This number doesn't mean that the shift is real. It just means there's a very unlikely chance you're making a mistake. The true test now of the new knowledge that you think you have is that you can repeat that performance. Okay, so you've done the one test, you've got the one set of data, you've done a hypothesis test. The p-value is saying that we've got a p-value of 0.035. It beats the alpha value that we're looking for, which would be 0.05. It's telling you there's a very good chance that this is true. However, for this to be real, the best thing you can now do is do a confirmation test. Okay, do a confirmation test. So if you look at this shift here, what have you moved it by? You've moved it by about 1.2 points. The mean shifted from 4.6 to 5.8. So what you would now want to do is to do the same thing again. You'd want to go back to the process. You'd want to take two samples. Do one sample set at 200, one sample set at 300, and you are predicting that you will get a 1.2 point. I don't know what the scale is in this case. Let's say it's millimeters. You will get a 1.2 millimeter shift in the result. If you get something around the 1.2, the confirmation has worked and the knowledge is true. You couldn't be this lucky twice running. Okay, so the hypothesis test, it's kind of telling you there's a really good likelihood that this knowledge is true. However, there's another piece of work to be done after this, and that's the confirmation test. But you cannot assume that when two samples are different, you created that with a shift, because two samples will always be different. You need the hypothesis test. You need, and get the right page. There we go. You need this thing, this 0.035, this little piece of mathematics. Now, we don't have to do the mathematics anymore. Once upon a time, this was hard work. Now it's the click of a button. But this is a really useful tool. It crops up in design of experiments, and that's really where I use this technique. I don't do one-factor testing. One-factor testing, like we've just seen, moving the temperature on its own, is a very slow way to learn how a process works and very inefficient. You won't actually know properly how a process works if you change one factor at a time. Design of experiments is the proper way to test, and DOE is full of hypothesis tests because it helps to tell us whether we're looking at signal, the change really made that effect, or we're looking at noise. It was just two samples that are always going to be different. That's why we use the hypothesis test. That's why we use the t-test. SPC Xl, the t-test.